Hello everybody. Today we're going to take a quick look at finding the length of a curve as opposed to what we've been doing, which is finding the area of the region between the curve and the x-axis. This is now switching from, I guess, what would be the equivalent of area to what is the equivalent of perimeter. Now, when you have a curved function, finding the length of that can be a difficult prospect. So all of this is based on the distance formula when you want to find the length of a line segment connecting 2 points. So just a quick example. When we go through, when we have 2 points and we want to go through finding the distance there, just to remind yourselves, the distance formula is based on the Pythagorean theorem, where the difference between the two x values would be your horizontal leg. The difference between your two y values of your points would be the vertical leg. So that is the distance formula. I'm not going to ask you to derive that again. It's not necessary. But when you have to find distance of 2 points, this is a coordinate geometry formula. You're just going to substitute in your 2x values and your 2y values. You're going to work out the math there, and you get the distance between the 2 points. Now, when we were finding area of a region between a graph and the x-axis on some specified interval, we were slicing that region up into rectangles, an infinite number of them, as a matter of fact. And we were adding the areas of all those rectangles together through the definite integral process. It's a very, very similar idea here, except instead of dealing with the area of a rectangle, we're going to be splitting the region up into little line segments, and then we're going to add the lengths of those line segments together to approximate the length of the arc. That's what happens. And obviously, the more line segments we use, when they get smaller and smaller and smaller, and we increase the number of them, our approximation is going to get better and better. Now, there's a little notation here. It looks like it's inside absolute value, but it really just means the length of the line segment from one point to another. Right. So what we're going to do, again, is add all of those lengths together. We're going to find those lengths using the distance formula. So distance formula on each one. And then we take the sum of all of those lengths. That's the approximate arc length. If I want the exact arc length, that's where we take the limit. Like we took the limit of a Riemann sum to get a definite integral. To get the exact arc length, we're going to take the limit of the sum of the lengths of all the approximating line segments. Now, we're not going to go through the derivation of the formula that we get. I just want you to understand that this is the process. That's what it's based on. It's not really necessary to go through the full derivation. But in words, the exact arc length is the limit of the sum of the lengths of the approximating line segments as you increase the number of line segments towards infinity. All right, so here's the formula. Like I said, we don't have to derive this ourselves. I just want you to understand this is based on the distance formula. And the integral part is when we're taking the limit as the number of line segments goes to infinity. So there's really two versions of this. There's when you're using x as your independent variable, and when you're using y as your independent variable. Most of these we're going to do on a calculator, but it doesn't have to be on a calculator. We might have to do these integrals by hand as well. All right, it's pretty straightforward. I want to do one example of each, x and y, and then show you where you might have to extend the process out with a question. Okay, so determine the exact arc length over this given interval here. All right, well, y is in terms of x, so we're going to find the derivative of y with respect to x. I'm going to call it y prime. That would be 6x to the 1/2 power. And then I just substitute that derivative into my integral formula with those limits of integration. At this point, I'm going to say we can go to the calculator and we could do this here. That's absolutely fine. With Math 9 on the calculator, you should wind up with 19 over 54. If you guys want to verify that on your own, that's fine. But if you take a quick look at the derivative over here and where that's squared inside the integral, that's right over here. When you square the square root of something, you just get the radicand. So that term right there would actually reduce to 36x. and that would not be that bad of an integral to do, just so you know. All right, with respect to y, now it's x is equal to some expression of y. Y is being considered the independent variable. So if we were to take the derivative of that 2/3, y minus 1 to the 3/2 power, using y as the independent variable, the 3/2 times the 2/3 is going to cancel out. We're going to subtract 1 from the exponent. We're going to get y minus 1 to the 1/2 power times the derivative of y minus 1, which would be just 1. So that's going to be our derivative. I'm going to show you the whole kind of process here. There's the derivative, the y minus 1 to the 1/2 power. Notice we're calling it dx dy. It's with respect to y. And then we substitute that derivative into the formula for arc length. So you get the 1 plus the derivative squared, which is in fact y minus 1. The 1's cancel out, you get radical y. When you set up your limits of integration and you anti-differentiate, that's what happens there. All right, the last thing here, because this is really kind of a simple process, the last thing is an extension of this. You might see questions where they don't just ask you for the arc length, but they'll ask you for a perimeter of a shaded region. And that's what's happening over here. So the curved part at the top of region R, we would use the arc length integral set up for that. But they're asking for the perimeter of the shaded region. So in addition to that arc length, you'd have to add that length, and that length over there. I'm not going to go through this solution for you here, but if you wanted to try this one out as well, there's the answer over there, and see if you can match it using the arc length formula and the lengths of the other three sides. That should be enough for you to handle most arc length questions. If you guys have any questions at all, just let me know. Give me an email and I will be happy to help out.